Welcome to the Explainer. Today, we're diving into a really powerful algorithm that helps computers find the hidden building blocks inside of all kinds of complex data. It's called non-negative matrix factorization. But let's start with a little puzzle. Imagine you have thousands of delicious, finished meals, but you have absolutely no recipe books. How in the world would you teach a computer to figure out the basic ingredients, the flour, the sugar, the salt, and the actual recipes for each and every dish?
Well, the answer is actually pretty elegant. It looks kind of like this. We take all our original data, all those finished dishes, and we call that matrix V. Now, the goal is to break that down into two smaller, much simpler matrices, which we'll call W and H. Just think of W as your big pantry of ingredients, and H as the specific recipe for each dish.
Okay, so let's put an official name to this process and really dig into what's happening under the hood.
It's called non-negative matrix factorization, or NMF, and it does exactly what we just described. It takes a big matrix, V, and splits it into two smaller ones, W and H. But, and this is the key, it has one very important rule. All the numbers in all three matrices have to be 0 or higher. No negative numbers allowed. And believe it or not, that one simple rule is its superpower.
Now, you might notice that little squiggly symbol. It's not a perfect equal sign, it's an approximately equal sign. See, the goal isn't to get a perfect copy of the original data. The whole point is to find a really good approximation using simpler parts. And it's inside that approximation that we find the hidden, or what data scientists call latent, structure that was buried in the data all along.
I know this might still feel a little bit abstract. So let's make it real. Let's walk through a concrete example from the world of text mining. So picture this. You've got a mountain of text. Let's say 500 different documents. And for each document, you've counted up how many times 10,000 different words appear. So how on earth do you even begin to figure out the main topics or themes buried in that massive collection? Well, NMF makes this whole thing pretty manageable. First, we just feed it our giant document word matrix. That's our V. Then NMF works its magic and splits it into those two smaller matrices, W and H. And finally, the fun part. We get to interpret W and H to find the hidden topics. So let's look at that first piece of the puzzle, the W matrix. This basically becomes our topic dictionary. Each column is a collection of words that are all related to a single theme. So you might have one column for technology, with words like computer, software, and data, and another for finance, with market, stock, and investment. These are our core ingredients.
And if W holds the ingredients, while H holds the recipes. Each column in the H matrix lines up with one of our original 500 documents. And the numbers in that column tell us the exact mix. How much of the technology topic, how much of the finance topic, and so on. You need to cook up that specific article.
The source material really hits the nail on the head. It says, we can consider each original document as being built from a small set of hidden features. NMF generates these features. It's just a fantastic way of saying it finds the building blocks for us. But you might be thinking, okay, but why is NMF so special? What's the big deal about this no negatives rule? Well, it turns out that simple constraint is what makes the whole thing so powerful and so easy to understand.
See, a lot of other methods can use negative numbers, so they might describe an article as being, say, 80% politics minus 20% sports. And what does that even mean? How can an article have negative sports in it? It's just weird, right? NMF, on the other hand, is purely additive. It only combines parts. It says an article is 60% politics plus 10% finance. That just makes intuitive, real-world sense.
And that right there is the crucial point. Because you can only add parts together and never subtract them, the results are incredibly easy for us humans to look at and actually understand. You're literally just seeing the components that make up the whole. Simple as that. Okay, so we've established we have this really intuitive and powerful tool for finding hidden parts. So where is it actually being put to work out there in the real world? Let's take a quick tour. The applications are just incredibly diverse. I mean, in astronomy, it helps tease apart the light from a distant star and a tiny exoplanet orbiting it. In computer vision, it can learn the parts of a face, like eyes, a nose, a mouth, just by looking at a bunch of pictures. And yep, it helps power recommender systems, figuring out the taste components that make you like certain movies or songs. And the list just keeps going. In bioinformatics, it's used to find critical patterns in our genes and even in cancer mutations.
In audio processing, it can literally pull a single voice out of a noisy room. And, as we already saw, it's a total cornerstone of modern text mining.
So it's clearly versatile, but how does it actually perform? You know, when the rubber meets the road, how does it stack up against other methods? Let's take a quick look.
So what we're looking at here is a sort of face-off between NMF and another really common method called principal component analysis, or PCA. Now, both of these algorithms are trying to do the same basic thing: find the most important information or variance in a dataset and separate that real signal from the random noise.
And you can just see the story in these graphs. If you look at PCA on the left, it starts off strong, but then it quickly just peters out. It kind of hits a wall and stops finding useful new patterns. But then look at NMF on the right. It just keeps going, consistently digging up more and more of the meaningful structure that's hidden in the data. It's just more effective.
And here's the other key thing. A lot of algorithms can get lost in the weeds, trying to explain every single random blip in the data. It's a problem called overfitting. NMF is smarter than that. It tends to focus on the true signal, the bright, important patterns, and it learns to ignore the random noise. That gives us a much cleaner, more reliable picture of what's really going on.
So, to wrap it all up, NMF is just this incredibly powerful tool for taking something really complex and breaking it down into its basic additive parts. And it does it in a way that's not only mathematically solid, but also wonderfully easy for us to understand.
And that really leaves us with a final and pretty exciting thought. We have this amazing way to find the fundamental building blocks of almost any kind of data you can imagine. The only question left is, what new worlds are we going to build with them?